Hey, Greg, long time no see.
Hey, just remember we're being recorded. So whatever we do, we be very careful about what we say.
That's right. Yes, it very loudly told me so as soon as I joined.
Mm-hmm. How are things going for you?
They're good.
Yeah.
The usual, you know.
Busy.
Yeah. New classes are hard, you know.
Yeah. How are you running your class? Are you running it asynchronously or synchronously?
Well, I synchronously, but lectures are recorded, so I assume that's what people typically do.
But you're pre-recording the lectures.
No, I give them live and then I record them as I give them with the questions and stuff.
Okay. Yeah, I got to get back on that. I did all the work to make my computer vision an online course. Like I broke the lectures up into 20-minute chunks and pre-recorded them and did them all consistently and all that. But I now have to actually do the little bit of extra work, meaning just give the data to the EP folks so they could actually turn it into an online course. And I just am failing at that.
Right. I mean, I think one thing that might happen is there might be an increase in like Coursera stuff because more people are learning how to run these things online, which is what.
Mm-hmm.
I mean, I have some friends in biostats who did very well doing Coursera in addition to their usual teaching load, basically. So.
Sure. Nothing like infinitely scalable teaching.
Right.
Hey, Kimia.
Hi, everyone.
I have to say, I very much appreciate your background. I keep thinking you're in Switzerland.
I keep wishing that I was.
Oops.
Yeah, Zoom always.
Is this actually Switzerland, this background?
I saw this Banff. It's in Canada, but I didn't take the picture, so I'll be happy either way.
But it's pretty well, the aspect ratio and everything is just right. Like you really could just be sitting up there on the deck.
Yeah, right. It's that's why I chose it. It's like I can pretend even to myself I'm in a really nice place. I do, like, honestly. I wish I was there.
I know.
Hi, Kimia.
Hey, Tony. Thanks.
I think.
Oh, I think Greg is frozen. I don't know if you guys have the same problem, but the internet has been a little bit spotty this past, I guess, week. I don't know if it's widespread or only my luck.
I haven't noticed anything myself, but I'm down in Northern Virginia, so I'm on Verizon, so I'm not subject to Comcast.
Nice. I don't have a choice but Comcast. Yay.
So it's 10:45, but I think, as usual, it takes people a little while to get here. So we'll give it maybe a minute or two, and then we'll take off. I see the numbers slowly growing.
Kimia, do you prefer questions in the middle or questions at the end?
In the middle, definitely.
Okay.
Yeah. It makes for, I guess that's what I miss from in-person like talks. There's a little bit more interaction. Otherwise, I'll be just talking to a lot of empty boxes on my screen, which is hard to gauge what's going on.
Yeah. That's the thing, right? It's everybody has now gotten into the turn their video off thing, and so as I told my computer vision course, you tell a joke and you have no idea if it was a good joke or a bad joke because nothing changes.
Greg, it's almost certainly a bad joke. So
That's That's always a good advice. Yeah, I'm guilty of doing the same thing. So, but yeah, something's missed.
Mm-hmm. Well, why don't I introduce you, and then you can take off. I'll spend a minute or so. That'll give everybody else that last little minute to walk downstairs and turn on their Zoom. So welcome everybody to the computer science lectures for today. The first thing I guess I'm supposed to remind everybody is this lecture is being recorded, as you were probably told when you logged into Zoom, but just so you know, we are recording this for posterity. It is a pleasure today for the computer science seminar to welcome Kimia Ghobadi, who is in fact a colleague of ours in the Whiting School from the Department of Civil and Systems Engineering. Kimia joined Hopkins relatively recently. Was it 2 years ago, Kimia, that you joined us?
Exactly.
As a new faculty member. She is a member of the Malone Center for Engineering and Healthcare, in large part because although she does work on decision-making processes generically, and a lot of this work is technical, she has done work that has applied the idea of optimization and inverse optimization to healthcare-related processes. She's also done a lot of interesting work on related to COVID and resource allocation, which I guess you're not going to be talking much about today, but if you go look at the Malone Center website, I think you can find some material about that. She's also the Associate Director for the Center for Systems Science and Engineering, which, among other things, has the fame and fortune of running the large COVID website that I guess Lauren Gardner was the lead developer of. Before coming to Hopkins, she got her PhD at the University of Toronto, and she was also a postdoc at the MIT Sloan School of Management. And in general, her interests are inverse optimization, mathematical modeling, real-time algorithms, which is something computer scientists like to hear about. So say real-time and you'll have us in the palm of your hand. Analytics techniques with application to healthcare systems and healthcare operations and medical decision-making. Her abstract today is type of learning optimization models, and I'm actually very interested to hear more about it. So Kimia, why don't you take it away?
Thank you so much for the kind introduction, and hi everyone, welcome to the talk. Thanks for being here. Greg, you mentioned that I'm not going to talk about the work we did on COVID, which is correct, but I'm going to do, I guess, like a few other talks in the next couple of weeks that they will all be about that. So if anybody's interested, I can always send you the information about those talks. Let me start to share my screen. And as I do that, I should mention that a lot of the work that I do is by my students. So really, they should be getting a lot of the credit. But I try to be a good representative today and tell you what they've been up to. All right. Does everybody see my screen? Awesome. And sorry, 1 second to see if I can change my pen to highlighter, to laser point. All right, that's great. All right, so and Ilya mentioned that, but I repeat it by all means. If you have any questions, please do ask in the middle. I like the talk to be interactive. And there are some parts of the talk will be a little bit more technical, so I try to step back. I'll be talking about learning optimization models today, and I'll tell you a little bit more about what it really means. So where I would start is that usually we have a lot of data, and there are different things that we do in data. So this is very general, like putting it in a very broad sense. We usually do either a descriptive analysis of the data, or we do predictive analysis, or we do prescriptive analysis of them. And I'm going to dive in a little bit deeper to say where's the space that I actually work in for this particular work. So descriptive analysis is usually when we want to know what actually happens, what the status of the situation or the environment is. In a way, we're really looking at in the past. So what was it that was happening in the past? As an example, I couldn't resist but using the COVID data, both because we've been working on it a lot and also because a lot of my other work is on it. But a good example of descriptive analysis is the COVID data that CSSE has, and all the different figures and graphs and charts that have been created based on it. It's a very fundamental step, really. Without it, we cannot do the rest of the analysis. Now, if I know my system, the next thing is predictive analysis. So the question is that, okay, I know what's happening right now, but what's going to happen in the future? And a lot of the AI and ML work, again, falls under this one. I'm painting this with a really broad brush. So I know there are a lot of different exceptions, but broadly speaking, that's what's happening. Going back to the COVID case, so for instance, I know what's going on, but I really want to know what's going to happen in the future. This is a snapshot from the work that Dr. Eli Klein has been doing. He's a PhD. And these show the prediction of Johns Hopkins hospitals. I actually grabbed, this is the latest one from end of January, and there are different trajectories that things can go, and you can look into every single hospital to figure out what is that you can expect for the future. So once I know my future, so descriptive and predictive, the other thing that I could be doing is prescriptive analysis. And prescriptive analysis, the difference between them is that now I want to know, I know my past, I know my future. What are my control points that I can change the future? What would be the right decision to do? What's the plan of action here? Looking at, for instance, the demand that every hospital is going to get for COVID. And right now we're really lucky where the number of cases are going down and we're not under a lot of stress. But at the times that there were surges, there would be a lot of questions. There would be a question of, okay, so there's a surge coming up. What do I do? Do I open new beds? Where do I open the new beds? In one of my hospitals, should I open beds everywhere? How many should I open? When should I open them? Should I close down all my other services to make sure that I can go on with this? COVID services. All of these questions are very relevant, and just looking at what's going to happen in the future will not necessarily give you the best answer about it. So that's where we do the prescriptive analysis. And an example of it is the work that I'll be doing a couple of talks on it in the near future. So in this work, we used optimization models, looking at every hospital, looking at how many patients they have now, how many patients they are expected to have, how long these patients stay, are they ICU patients, are they normal patients, and what we can do in terms of the capacity. How can I manage these patients? I don't have any control over what happens in the future, so I cannot really say that the number of patients should go down. I don't have control of it. I also don't really have control over where the patient shows up in ED. So if they live in an area, they would just go to that area. And usually there's a huge imbalance because of the disparities and because the healthcare capacity might not be aligned with exactly what goes on the local level. So for instance, in areas that may be socioeconomically on the lower level, they usually don't have a lot of healthcare capacity. So especially their ICU beds, they would have very few. Then what is it to do? What you can do is that the way that you can control is that you can control where to meet your demand. So where to take care of these patients. So that's the idea, that's the decision point. The patients arrive, my decision is where to care for them. And you can send them from one location to another one. And that's behind the optimization that we do. So for instance, in this one, every dot is a hospital. If it's green, they have capacity. And I actually ran this yesterday. And this is from how things look like in the next couple of days. If they are orange or red, they don't have capacity. And what you would do is that there are a lot of patients coming in. You just will them over to locations that do have capacity. And there's a lot of different constraints and conditions that we consider to make sure that this is all practical and implementable, and you can get insights to actually make your decision based on that. For anyone that's interested, we have a website that I have it here. We try to make it as user-friendly as possible. So go ahead and have a look. So that's a long way of saying that prescriptive analysis are there to really inform your decisions. And it's a lot of times it's something that we can learn from the data. And that would be where I focus. So a lot of what I'm going to talk about is not going to be about descriptive or predictive analysis, but about the prescriptive analysis. Traditionally, how we solve prescriptive analysis is optimization. There are other ways. There's also simulation and other methods, but optimization is one of the main ones. And when I say optimization, I mean you have a goal, objective, you're trying to minimize or maximize it, subject to a set of constraints, and you have decision variables, which are X here. So this is my decision variable here. And once I solve it, I arrive to the decisions that I wanted to know from the beginning. So now that we're focusing on this one, what is it? How is it that we typically think about optimization problems in prescriptive analysis, and what's the difference between? Because a lot of times when we think data, we think predictive or descriptive. One good thing about predictive and descriptive is that it's highly data-driven. It's almost entirely data-driven. You look at your data and you decide what's going to happen or what has happened. And the outcome that you hope for are actionable insights. What did I learn from my data that can actually help me in real world? In prescriptive analysis, it is somewhat data-driven depending on the method that you use. But if we're thinking about optimization, it's mostly knowledge-based. I decide that this is how many days that the patients will stay. Or if I'm thinking about a treatment for a patient, I decide that these are the doses that I want the patient to have. So the blood pressure should be between this and that. So there's a lot of knowledge, expert-driven knowledge that come in, and you formulate your problem based on that. Eventually, what you get is really good, though. You get your optimal solutions. You don't just get insights and question whether or not they're actionable. And they're usually pretty interpretable because you have written your problem pretty explicitly. So now when I think about, so that's really good about optimization. That's also what I like. But when I look at the traditional optimization, a lot of it is knowledge-based and a lot less of it is data-driven. When you think a lot of data, you don't usually go, oh yes, this is the best thing for optimization. If you think an environment has a lot of constraints and you know a lot about it, then you think optimization. The other thing that's about optimization is that we usually assume that the formulation is pretty certain. I know the formulation, I know my F and G, I know exactly how things work out. And in reality, it's not really correct. So those are the parts that I'm going to focus on. I want to know how I can leverage data, because a lot of times we do have data, to learn what my optimization parameters were, my F and G, whichever that is unknown or partially known. And once I know them, once I can write an optimization problem that corresponds with the data and the real world, then I can just go ahead and solve that optimization and simulate the decisions. I arrive on my decisions. So that's where I set off to work. Now, let's see. So I have data. I want to get to my decisions. and I'm thinking about optimization problems that have some unknown parameters, and I want to predict these unknown parameters from data. If I just gave you this definition, one of the first things that might come to mind is that, well, why don't you just use machine learning or another prediction method so that you can solve it? Like, we've done it, we know how to do this. So why don't you do this? We do sometimes. It's a good thing. There are cons and pros. The pro is that it's data driven and you can train your decisions. So there's really no optimization. And a lot of times we do end up doing that. The cons is that when it's very data driven in the traditional sense, it's hard to have knowledge-based parameters. So if I know that, and that happens a lot. So if I'm looking at my, let's say, population, and I know that, let's say, 20% of my populations are minorities, but my data is mostly from the other side. If I'm just data driven, I'm limited to my data. I will not be able to have that in my model. But if I know that 20% should be something else, I can have it as a constraint in my model. So that gives me more power. So that's the, yeah.
Can I ask a question? I'm sorry.
Yeah, please.
So, so you've made, I mean, this is still pretty high level, but you've made this big distinction between predictive versus prescriptive stuff, which sure sounds like an awful lot like association versus causation to me. But you also said that both of them are solved by optimization, because, you know, when you train predictive models, you also use optimization. And so what to you is the crucial distinction? Because one could imagine doing optimization wrong and getting bad decisions out of that, right?
That's a really good question, and I guess that goes a lot like higher level than you and I, like, yeah, between our fields and how we're defining ourselves and what terminology we're using. To me, the distinction between is that what's the output? Do I end up with decisions? And I'm sure, like, yeah, in optimization, I know exactly what my decision is. But if I'm using optimization in my neural nets, it's not the decision, I'm just recognizing something, or I'm classifying something. So if I'm classifying, I would say that it's prediction. You can tell me, like, yeah, if I'm wrong, or I should be thinking about it in a different way. But in my mind, that's how I'm distinguishing between them.
But surely it's more substantial than just like having an output being a label versus an output being a decision, because it's just, I just call things different things, but I'm still fundamentally solving the same kind of problem. So there must be more to it than that, right?
There's probably more to it as well. So another way that I think about it is that so by the output, I basically gain all the questions that answers all the questions that I had. And again, this is like we're going around the terminology which are pretty vague, and I'm not aware that anybody has defined them that explicitly. This is the best that I have found so far. But let's say if in optimization, if I know my X, I know everything about my problem. There won't be any unknown about my problem. Doesn't matter what happens in the future. I have something that is set. I know my objective. I know my constraints. I know my optimal solution. Everything's set. Versus if I know the label for something, that might not be the exact question. So I will use that to probably answer some other question. So there might be steps that I can do afterwards.
Okay, thanks.
Does that, okay. But a really good question. I think like it's more of a debate. Like, yeah, I'd love to like someday grab a drink and go talk about all of these and the philosophy and how to really position ourselves. And I do think that among the different ways that we think about problems and use data, a lot of times we're complementary and there's a lot of overlap, but there's not a lot of distinction and I guess transparency between the different ones. So that makes it a little bit harder to integrate different fields together and bring in these different tools and figure out what's best for which situation. Good question. So let me move, go on with, go back to the presentation as in, so if I have data, I want to learn my decisions, I can use AI methods or machine learning methods to Elia's point, but there might be something that I'm missing. Another way that we can think about it is that, well, what if you use machine learning to learn your some parts of your optimization and then use optimization to solve your problem? That's also good. The really good thing about it is that we know how to do it. I know how to get data and apply machine learning methods on it. And I know how to run my optimization. So really good thing. But the danger is that there might be misalignment. So what the machine learning or the AI might get for the optimization might not necessarily be what the decisions will eventually be about. So that disconnect can hinder what we're doing. And again, I would love to have conversations about it. And let me go to the next slide, and then I'll make another point. So what we are proposing is go from data. So I know that what I wanted to do in this particular set of problem, these decisions are a result of an optimization problem. So really, I want to find that optimization problem. So one way that I can do it is to use another optimization problem to find or learn the original optimization problem, which is my goal. That we call inverse optimization because you're going in a reverse direction. You usually have some observations of your decisions along with some other data that you might have. So you basically know some of the elements of your X star, your optimal points, or something that is very close to the optimal. And you're trying to figure out, so I should have showed it here. And you're trying to figure out what your F or G is. And for doing that, we solve another optimization problem. So whenever I say inverse optimization, that's what I mean. An optimization to find out what the original optimization was. Now, let me make the point that I said that I would make by no means, I think that this is something that should be applied to every problem. I think there are a lot of problems that we have good methods and we should keep doing those methods. To me, the general AI, machine learning, all these statistical methods, they're really good. They apply to a lot of different problems. They're a little bit more of a like a big knife, like a blunt knife. You can apply it to everywhere, but you don't have a lot of control. And the way that I see it, optimization is smaller but sharper knife. You can sculpt what you want. So if you have extra knowledge that you can plug in, it's excellent place to have it. So again, like I think there are particular problems that lend themselves really well to optimization. And the inverse optimization is, so if you think about AI, and let's for now assume optimization is part of AI, there's a whole bunch of debate on that. I'm not going to get into that. So optimization is a small set. Now, inverse optimization makes it a little bit bigger because you can use some of the data, you can use some of the prediction methodologies and statistics methodologies and bring that to the optimization. So that opens up the field a little bit and connects the two a little bit more. Any questions? I'm gonna like give an example of how I'm thinking about this and what these decision data, like I stayed really high level, and what they actually mean.
Kimia, would it be fair to say that part of the distinction that you were talking about before is between having interpretability and the ability to explicitly incorporate counterfactuals into a model?
Definitely. That's one of those, and both in terms of how we write the model and also in terms of the output of how interpretable it is.
Okay.
Because like if I write my optimization problem, I have gained or have incorporated extra knowledge that makes it more explicit, rather than if I just look at the data and try to figure out what the data says and try to just build a structure that captures that best. That's more of a, I guess, I'm gonna say not supervised, but like that would be the wrong way, but like going to it like more blindly, as in for an optimization, you usually have a lot of knowledge and you use your data just to get to the decision. Does that make sense? And also the way that I see it, like optimization usually comes as the last place. So you do descriptive, predictive, all the other type of analysis, and that's sort of like the last step. So what would be the optimal solution given that I've done all this other work?
Okay, so is the challenge doing it end to end essentially, that incorporating both types of?
That's one of them, yes,
Okay.
yes. And as I said that, I realized that we do use optimization in prediction, so there's like a back and forth between them. So there's a lot to unpack here. Like the whole field is too big to really like, this is an attempt to capture it. I do not claim it's exactly this. Any other questions? All right, thanks Thomas for the question. Okay, so I've been talking about data, decision, etc., but let me give an example to make it a little bit more, I guess, touchable of what I mean. So we do like diet recommendation is, I guess, one of the first optimization problems that came along, and they're still relevant. They're really not solved. I don't think anybody comes in and say, I have the diet problem that you can always have, and this is the best ever. We try our hands on diet problems, and the way that we think about it is that you want a diet problem that people can adhere to it. And in specific, I'm going to talk about this a little bit later, but specific, we're thinking about patients, chronic patients with hypertension, diabetes, heart disease, kidney diseases, etc. And as part of their medical treatment, they have to adhere to these diets. But usually what we do is that we just give a diet to everybody. We say more greens, more vegetables, don't eat any sugar, and everybody tries that with the best intention at the beginning, but eventually people fall off at different locations because it doesn't really personalize it to people. So let's give an example. Let's say I have person A, athletic, burns a lot of calories and sodium, and has a sweet tooth, and maybe they're like milk, stews, nuts, and cake, just as an example. Let's say you have person B, very like maybe a parent and a professional, doesn't have a lot of time, goes for fast meals whenever they can, and they like cheese, but they don't like nuts. And they eat sausages, beans, pizza with the kids, and vegetables. So try to be healthy, but really cannot do that much. If I just look at the diet problem and try to give them in the optimization sense or in the general sense that we do it, is that let's say I want to, for both of these, I want to minimize calories. It could be minimize whatever, maximize protein, minimize sodium, can go anywhere. And then you have some constraints on the nutrients. Let's say want to limit the sodium. Usually that's the big one with hypertension patients and diabetes and a lot of them. And let's say want to improve or increase the protein that these people are eating. If I just run that, whether just looking at the diet or I run the optimization, I get something that's exactly the same for both of these guys. Eat fish, eat nuts and fruit and vegetables. But if you look at it, it's not exactly what they like, and doesn't really represent the different type of lifestyle that they're running. So what would be the right way? So if I wanted to do optimization, I want to optimize this diet for these people. What would be the right way to do this? Should my objective be minimize calories? Should I change some of these? Is there something else I can do to this optimization to figure it out? And that's where the inverse optimization comes in. Can I recover? Can I learn an optimization problem that's suitable for this particular problem? So in this case, let's say I want to personalize it to make the diet more palatable for them and lifestyle to eventually improve the adherence to their diet. And if I do that, just an example, it would be very similar and could have like different levels of similarity to what they're doing right now. So the observations, I would call them the observations, how I've seen they eat. So maybe the first person I tell like, yeah, eat yogurt that has more protein for you. And you know what, don't eat a lot of cake. In person B, I say, well, go easy on the pizza, vegetables if you can add fish. So it can be as close to the observations and what they like, or as far from it. So maybe this is where I start, and then as the person get used to it, then the next one, then I can move it to something that's closer to the optimal or the traditional optimal that we have. So move towards a really healthy diet. And as you saw for this example, and in general, we're trying to move away from one size fits all and one optimization solves it all, and use the data a little bit better. And there are two main things in the problems that I usually think about them. They're highly constraints, and they can be data driven. So diet is one example, and I'm going to give you some examples of this, but you can also think about how doctors prescribe treatments or medication for patients, or how doctors decide on what's the right, do I admit these patients, not admit these patients. I mostly talk about healthcare, but they can be anywhere in terms of the policies, or even in computer networks systems. We're doing a work that we're looking at how when there is uncertainty in the data packages that are come, and then some of the links are failed, where those are usually, how would you better compensate for that when it happens? So sort of like learning the optimization rather than doing a really conservative optimization. I'm happy to talk about that work offline if anybody is interested. Coming back to it, the diet problem, example of why it's highly constrained, and that's important to have highly constrained. If it's not constrained, you can just run typical ML problems. But for instance, for diet, there are nutritional constraints. For every food, we have constraints, like maybe sugar should be between this and that. The different food types have constraints. So let's say I'm trying to like cheese or like dairy, like only consume it between this and that. And every patient might have their own constraint depending on the condition that they have. So a lot of these, as you see, these are mostly knowledge-based or expert-based. So these are not things that I would necessarily get out of the data. But at the same time, it is data-driven. And the assumption is that I can observe some of these decisions. So for instance, for the diet, I can observe the food that this patient has been taking. And that part's more data-driven. That part is what was actually happening in reality. Or if you think about doctors making decisions, what has been their decisions? Can I look at the historical data and then look at what I have as a clinical guideline and combine the two of them together? All right, so with that, I'm gonna go to a little bit more details of defining the problems. Are there any questions so far?
I have another question,
Yeah.
which may be related to my earlier question. So it really sounds like a lot of your examples seem to be very closely, I mean, maybe I'm confused, but they seem closely related to, offline, off-policy reinforcement learning, where you observe people do decisions, and you would very much like to do, find an optimal way of making those decisions. And so there's a very, very rich literature and all that stuff. And I'm just wondering what the relationship is of inverse optimization, as you think about it, to that kind of stuff.
So we're just starting that. So I would say that would be complementary to that. So the decisions that we're thinking about, as you mentioned, there's also a whole lot of literature in economics and how those decisions are made. The way that I would distinguish it is, in this case, I know that there was an optimization that resulted into this, or at least I can make that assumption. So I can make the assumption that people are logical. So sometimes you do make those assumptions, sometimes you cannot. And go from there. So I recover those optimizations. So if that's not an assumption that is relevant or applicable, I would say that doesn't really do it. But if this is an assumption that is applicable, I would say inverse optimization might provide insights that are complementary to the current literature.
Okay, so in other words, the observed decisions are the result of somebody optimizing something, but you don't know what it is and you want to find it out.
Exactly. So, so if I'm randomly deciding, I don't know where to go, it doesn't really count because I'm not really optimizing anything. But if I'm a doctor and I'm trying to give my patient the best medication or treatment, I am trying to optimize something. So it's reasonable to think that there's an optimization going on.
Okay, got it.
All right. Awesome. Good question. So looking at it in a little bit more formally. So forward optimization, and when I say forward optimization, is the typical optimization that we think about it. Usually I know my goals, objectives, I know my constraints, parameters, and I'm trying to find what is the best solution, what is the best decision that I can make. And I'm going to look at this for linear optimization specific, and that's where most of the inverse literature has been going on. And I'll tell you about like the complexities in the inverse optimization. So if this is a linear optimization, my objective is usually C transpose X, constraint is a matrix A times X greater than B. That's the typical way that we think about it. And really my parameters are just the coefficients that are being multiplied by X and my right-hand side B. So if I have all of them, I know exactly what my problem is. If I don't know some of it, then I have some unknowns in my problem. And just graphically, you might have your constraints, your feasible region, you know your objective. Let's say I'm looking at the objective when it's increasing, so maximizing, and I find my optimal solution. Now the difference is that what if I don't know these parameters? Sometimes the parameters are uncertain. For instance, how much food did I have? Was it exactly one serving or a little bit more, a little bit less? Sometimes these parameters might be just hard to find. For instance, in clinical medical decision making, so if I go over every lab and every test and I'm really careful about it, maybe I can find some of these, but in reality, that's so hard that you can't really do it, and you're not really sure that every test is done for every single patient. Or sometimes they're just unknown. We don't know, and that happens quite often. Going to the diet problem example, I don't really know what it is that the patient is trying to do. I know they're trying to maximize the palatability or their own adherence to it, but they don't really know what are these different things, the utility function that the patient has. So inverse optimization does the opposite. It tries to look at some of these decisions and infer some parts of the problem. So for instance, if I'm looking to, I say infer, but I don't mean inference analysis really, like it's just like recover. It's just a terminology that we casually use without really having the meaning of the inference. So if I wanted to find what my objective function was, let's say I know my constraints, I know my optimal solution, and I would want to find this one. So this is the typical way that we do inverse optimization. I may not know my constraints on the other hand, so I don't know what my feasible region is exactly. I may know something about it, but not exactly. I know where my optimal solution is. I know what I'm trying to achieve, but where are my cutoff points? So you can think about it as medical guidelines. I know what the doctor is trying to do, but what is the right minimum and maximum for different doses, really? So in this particular talk, I'm going to talk about linear optimization. I'm going to focus only when we're trying to recover the objective function or the utility function, and trying to find that forward optimization that would help us. Now, in that sense, we use inverse optimization, and inverse optimization has been developed. Me and other colleagues, we have all been working on it. But in general, inverse optimization is rather new. It only started in the 2000s, really picked up about 5-6 years ago, and we're sort of like going through the infancy and like improving the methods as we go. There are a couple of assumptions that go into inverse optimization that we will try to improve them during this talk. One of them is that inverse optimization can recover the constraints or the objective with one or very few observations. That's a really good thing. When we think data-driven, we usually need a lot of data, otherwise I can't really say anything. But inverse optimization can do it with only even one observation because I know a lot about my problem. I'm assuming it's an optimization. I know the constraints. I know other things. So I have a lot to go on. But at the same time, it's not the best thing because what if that one decision was not really a good decision? What if there are different types of decision for different situations? So making it larger is really good. The other thing is that inverse optimization usually thinks that what we have observed is optimal or near optimal. Again, and assumes usually that the corner point is the optimal solution. So there are some concerns with this type of assumption that we'll try to address in the next slides. And how does it in general work? It's we minimize some sort of optimality error. So let's say if my observation was here, I would try to make it over here. We use the optimality conditions for those who know KKT conditions, Kirsch-Kuhn-Tucker conditions, and there are some norm conditions because usually you have a lot of flexibility. You want to pick the best problem, so you don't want redundancy. So in general, this is how inverse optimizations are written. Now, what we are going to do, so from next slide on is more of a details of a specific work that we're doing with my students, Frazine and Ferdine, and actually they've done a lot of the slides, so the slides will be a lot better than what I have shown so far. And we try to look at these two assumptions that are made in inverse optimization and try to improve on them. So one of the things is what we consider as optimal solution. So if I have observations, some of them could be outside my feasible region. So remember that I assume I know my feasible region. I don't know my objective function. I don't know the utility function. Maybe some of the observations are outside. Think of it as diet. So a lot of times the diets are pretty hard, and you might have an observation that the person ate a little bit more sugar or a little bit less protein than they were supposed to. Some of the observations are also inside, and some of the observations might also be right on the boundary. Now, how do I define the optimal point? If I know that my constraints are set, my optimal point will be, we will assume anything that is on the boundary. And if you have any other observations, you would try to get them to the boundary as much as possible. And the distinction is that you can only think about the boundary as your corner points, or you can think about it as anywhere in the boundary. Jumping a little bit ahead, but we really want to think about it as anything in the boundary, which is the next point that I'm trying to make is, where is the optimal point? Let's say you have a whole bunch of observations. Your optimal point, if you're thinking about the boundary, can be anything. It really depends on your observations, and could be corner points, could be different different constraints that you have. And depending on the observations and other things that you know about your problem, you can decide about one of them. So in this case, I would argue that given these observations, this is probably the optimal point that you wanted to arrive. Not this one, not this one, not anything else. So one of the things that we do and think about is that reducing the problem not to recover the optimal boundary points, rather than trying to reduce the distance to a corner point and find out the utility function, the objective function. So that's the first thing. So anything on the boundary will hold. Another thing that we do in inverse optimization, there are actually a whole bunch of them that we think that we can improve on. One we talked about is usually based on single observation. That's not necessarily the best, because if you think about single observations, and in traditional inverse optimization, we always recover a corner point. You might actually end up with something that is further away. The other thing is that typically only feasible observations are considered, where in reality, looking at how people make decisions, doctors, patients, diets, a lot of them are also infeasible. So adding the ability to do infeasible observations, that's also a plus, and that's what we do. And let's say if I only had these observations, a patient was trying to do a good diet, but they weren't really doing it well, they were trying to reduce it this way, then maybe the optimal solution for them will be this one, which also meets all the dietary conditions that they need to hold. The other one is that traditionally in inverse optimization, we try to recover the cost function. And the cost function can be parallel to one of these constraints that I'll talk about this a little bit more. But that might mean that we end up with a point that is further away, because if you recall, when we do, and this is the same thing with inferring the corner points, I make both these points at the same time. If you recall, when we have linear optimization, we usually solve it with simplex. If we're using with simplex, we usually end up with a corner point. And a corner point, so if I say that this was the direction that I was trying to improve, and this is a good direction, that's not a bad direction, I'm hoping to get this point, but if I solve my optimization problem, I might end up in this point. So there's a lot of limitations if we only look at corner points, and it makes it unstable. Like sometimes you might end up in this one, sometimes this one, because they both have the same objective value. So we try to address these. With a methodology, we call it inverse learning. And we focus on finding the optimal solution and not necessarily finding the objective function and then solving the forward problem and then finding one of the boundary points. So that's one of them. So for instance, if this is my observations, I could find this one. If these are my observations, I find this one. So sometimes I find something that is middle of the boundary, sometimes on the corner point, but anything on the boundary, I consider it as an optimal solution. We assume a lot more observations, and because we have a lot more, we can reduce outliers interventions and how they will affect the problem. And another thing that we do in our model is that we can create a trade-off and control it between where the observations are and how many. So at optimality, different constraints become active depending on the corner point that you have, and that's something that we usually would like. Then we can create this control between them. Do I stay very close to how I was observing these people to diet and their food choices, or try to really push it to get the maximum protein and also get the maximum fiber and also get the minimum sugar and the minimum sodium, etc. The more constraint that I require to bind, the further I'm probably getting from these observations. And how do I control between the two of them so that I can sometimes be close to the observations, maybe at the beginning, and then sometimes going closer to what I would have eventually like these patients or these process to do. To do this, we think about the forward problem a little bit differently. We split the constraints that we have into two parts, the ones that are relevant to the problem that we're solving and the ones that are trivial. If you want to think about the diet, so the trivial constraints could be that, well, no food can be negative. I cannot eat negative amount of food, so the number of dishes should be positive. But relevant constraint maybe for hypertension patients will be that your sodium should be between this and this. Do not go anywhere else. Graphically, if you want to think about it, so some of these edges are more important than other edges. So we make that distinction, and this distinction doesn't really change the generality of our problem. Still pretty general. You can do this with any problem. So now how do we actually do it? I'm going to give you a little bit of math. Let's say we have observations. Let's say I have k observations of decisions that have been made in the past. Then I want to minimize some measure of error, and this error could be the error that we're creating to the optimal solution, and also how far we are from the observations. So there are different ways to define it. So I'm not going to get into the details, but happy to talk about it offline. Then if you remember, in inverse optimization, we want the KKT or optimality conditions to hold. One of them is forward feasibility. So these are just the two constraints that we introduce in our forward. I want the problem to stay within my feasible region. There's nothing here, and this Z or Z here is usually we think about it as X. Now we have Z because we're looking at only one point to infer as our optimal solution. Another part of the optimality condition is strong duality, which is the first one, and also dual feasibility. We just add them in. We have them as part of our model to make sure that whatever that we infer will end up on the boundary. So this is how we're ensuring it's on the boundary. Then we add another condition we call learning conditions, and the reason for this condition to make sure that we recover only one point. If you have thousands of observations, you don't want to project all of them to the boundary, because then you would have thousands of projections on the boundary. You want to have only one of them. So that's a learning condition. we have some normalization condition to make sure that we don't get duplicate solutions. And this is in general how we do the inverse learning. So this is the optimization that we solve to recover the original optimization. And we can show different properties for this, including that this is feasible and well-defined, and you can actually solve it and for the problems. Any questions? All right, cool. So another thing that you might want to notice that I wrote it here is actually a very nice optimization, but it could be nonlinear, and as a matter of fact, it's it's generally nonlinear. The nonlinearity can come from two parts. One is the normality condition, and that sometimes we can get rid of it if our matrix has some properties. We don't really need a normalization condition. So this one is solvable. The one that usually gives us trouble is the bilinearity in strong duality. So here C is a variable, Z is a variable. I'm multiplying them together. That means that I'm going to end up with a problem that's non-convex. And we show different ways of how do we usually solve it, because if your problem is non-convex, you don't know if you found the global optimal or you found just a local optimal. One of the ways that we can solve it is that we can show that the optimal objective function that we have will be parallel to one of the important constraints. So in this case, my C vector will be close to one of my A's, and A being the columns of my A matrix and one of these constraints. So jumping ahead of this, just looking at the figure. So let's say the greens are the relevant constraints. Then I know that if this was my my correct objective function, this one Z1 will be the optimal solution that I find. If this one's the correct one, Z2 will be this one, same one, Z3. So you will see that all of a sudden we have an algorithm that is iterative. I can take every single relevant constraint that I have, and I assume what if this was the optimal objective function. I find the different Z's that I need, and then because I'm minimizing the error, I would just find where the error is minimized. So now we have a methodology that is polynomial to the size of the relevant constraints that I can recover it and solve my previously bilinear non-convex optimization problem. Now, what are the other things that we can say? So once we realized that, and that was the first thing, it's like, yeah, good, we can solve it. And then we realized that we can do more. So one of them is that how many of our constraints are relevant constraint we can bind. And I alluded to this a little bit, how far are we from the objective function, from the observations to really requiring a lot of these constraints to hold so that we're at eventual optimality, let's call it. We modified the problem. I'm not going to go into that one. The way we call that IL stands for inverse learning, and then P is the number of constraints that we enforce to bind in at optimality. We just add a constraint for it. So if I want only, so let's say if these are my observations, if I only wanted one of my constraints to hold and I solved it using this algorithm that I just said in the other slide, this will be the optimal solution. That's the closest, let's say, for my observations. But what if I wanted at least 12 of my constraints to hold? In that case, I would end up in this corner point for this very simple problem where I'm not going to lose how far I am or my optimality, but I would find something that's a little bit better. Now, and we can continue doing that depending on how many we have. Imagine like we have multi-dimensional. It's usually not a nice 2D graph that we're looking into. And we can always show that the distance of the first one to the observation is no greater than the distance of the second one. So everything makes sense, everything is well defined. We make sure that everything's fine. Another thing that we can add is that, all right, so maybe I have a lot of relevant constraints. So minimize sodium, sugar, protein, maximum protein, fiber, minimize fat, trans fat, etc., etc. But they're all relevant. I don't really want to, I want to hold as many of them as possible, but maybe based on what I'm doing, some of them are really preferred. So let's say this one is preferred. A preferred one is that at this point, maybe I'm an athlete and I'm trying to maximize my protein. Or maybe I'm a hypertension patient and I'm trying to minimize my sodium. That's my priority. That's the first thing that I want. But that doesn't mean that if I find a solution that is minimizing sugar would be a bad one. So it's still relevant, but maybe not my preference. In that case, we just we modify our formulation, and then we can find a point that also holds for our preferred constraints. So we're trying to maximize the number of preferred constraints that we have. So all in all, that sort of like shows the distinction that we have of how data-driven I am. It's if I had only observation, I look at the average of the observation versus going to the inverse optimization, then looking at the constraints that are relevant because I'm projecting to the boundaries, and then looking at the constraints that we are preferred. So we can do the trajectory on all of this. I'm going to give you a summary of it. So we find the closest point to the optimal solution, and we can find this whole range of the solutions. And if I have additional things that I know compared to the so compared to the optimization, that I know some of these constraints are more important than the other constraints, we can always put those. We did our due diligence. I'm not going to go into details of it. This is just a 2D representation of how things look like. I'm just going to jump into the results and the parts that you may want to pay attention to. So anything below this line is existing models. The top ones are our models, and MIL or is multi-IL is the one with the blue, also the preferred constraints. What you want to notice is that as I require more types of constraints to hold, I probably get further away from my observations, which is expected. And my objective value might also go up because that's also related to, well, the way that we wrote it is related to how far am I from my observations. Now, probably the one thing that you wanted to know is that, like, how did it work with the diet problem? So we did apply to the diet problem. We got the diets from NHANES, about 10,000 patients. They interviewed them for 2 days, and they have demographic, existing conditions, etc. So we use that data, and we'll look at the DASH diet. So DASH diet, for those of you who don't know, it's a diet that's usually recommended to hypertension or and diabetes patients. It reduces the sodium quite a bit. It's a fairly restrictive diet. So this is a snapshot of how it looks like. And it will say like grains, this much, vegetables, this much, and gives you like different calorie targets. And this is what the doctors will actually tell the patients. They would say, oh yeah, you probably need this much calories, and this is what you should aim for. And nothing much more than that will go. So we use that DASH diet that is actually being recommended, and to have to sort of like go from like grains to actually talking about different nutrients. We use the guidelines from USDA. So we ended up with different targets calories. We ended up with lower bounds on upper bounds on different nutrients. So calories, this much, carbs, this much, etc., etc. So that's the setting of how we did this. Then we ran it, and I'm showing you the results. So these are the, in terms of number of servings, and these are the different types of food that we had. This is from over 200 patients that were all female and were 51 plus, and they were worried about their hypertension. The box plot that you see is their observations, and the green ones you see are the relevant constraints that are important, and the blue ones are also preferred constraints. We try to hold the preferred constraints, and we try to hold them like only one up all the way to 4, and then one preferred constraint all the way to 4. So that's how you should be looking at it. What you want to really take away from it is that if I look at things that are not really bad, but not really good, I mean, cheese, cream, you usually want to be careful about them, but don't really, like, they're not really bad food. We try to, the model stays fairly close to what the observations are. So how the patient was doing it is fairly close. If you look at stuff that are typically assumed to be good for the diet, so the seeds, grains, fruit, you see that the observations are pretty varied and usually much lower than what the models will suggest. And this is in line. You would expect that you would try to improve them a little bit and give them a little bit more of the good stuff. The bad stuff, the patient might be having a lot of them, and then read the recommendation as well, try to do it a little bit more moderately. So this is how the optimization and the inverse learning has been working for this set. And we'll look at how far they are from the observations. And as we hold more constraints, we go further away from the observations. And way further, this is like how many servings away we are. And all of these sort of make sense. So everything seems to be in line. Another part of this solution that might be important, we talked about the constraints that hold at optimality. So these are the different constraints. So you see like diet, sugar, fiber, sugar, fat, etc. And we have the same as hold the relevant constraint, hold as many preferred constraints as you can. And you can see that if we hold the preferred constraint, so for instance, here we have the preferred constraint to be carbs, minimize saturated fat and cholesterol, and minimize sodium. And in the blue, then we try to get there as much as possible. So the first one that holds is sodium. Then in the next round, the next one would be this one. So then we can hold with saturated fat, and then oh, sorry, I'm doing it wrong. So cholesterol, then saturated fat will be minimized, and carbs will be minimized, and sodium will be minimized. So all of it to show that all of this actually makes sense, and we see the same results hold for everything. So I'm going to conclude. It is a powerful tool for specific type of problems that do have optimization as the forward. So we are trying to recover the forward optimization. And what we do is that we navigate the boundary space. So we're going a little bit further away from traditionally how the inverse community we think about it to in reality, how does it really mean? And we can control the trade-off between how close am I, how just data-driven I am, to how knowledge-driven I want to be. So can I go between them, between my two goals? And for the diet problems, we provide a range for them rather than just telling them, this is what you need to do, good luck. That brings me, and by the way, all of this is available, and we have a web tool. The data is available for free if anybody wants to use it for courses or anything else. And there's a web tool that you can play around with different models. I'll put the links to the chat. And thank you so much for listening. I want to acknowledge my students, Farzine and Ferdine. They did all the hard work. I was just sitting and chatting with them. That's how much I did. And if there are any questions, I'll be happy to answer.
Thanks, Kimia. It was great. And actually kind of went in a direction I hadn't completely expected. So it was a good talk from that point of view, too. I thought you were just going to tell me, I can now learn how you think, and then I can build a machine that emulates the way you think. But you're actually telling me I can both build something that emulates how you think, but I can also tell you how you should think, and then try to change my behavior, right? Like make my diet closer to what it should be as opposed to what it is.
Yeah, exactly. Yeah, that's funny. Actually, like when we first started, I was like, oh yeah, we can emulate how people think. But yeah, it turns out this is the better way to go, or at least more practical for what we have. So yeah, well observed.
Mm-hmm. Questions,
I
anyone?
have a quick, yeah, this is Todd McNutt. I have a quick question. So oftentimes, at least in our radiotherapy, and I'm sure we'll talk about this more tomorrow.
Yeah.
Oftentimes when we are looking for an optimal solution, that solution, like in our case, would be this three-dimensional matrix of dose data. But the objective function itself is feature reduced. In other words, it's you know, each component of our overall objective function is calculated based on, you know, all the small pieces of data. So there's a feature reduction process. and those reduced features are probably what more have the boundary conditions on them than the final overall result. And I'm just wondering that in your models, if you have a reasonable way of sort of doing feature reduction that's understandable, that could be kind of put in the middle there rather than going at the direct optimal solution as defined by the sort of raw data instead of the objective functions derived from the raw optimal solution. Did that make sense?
I think so. I try to, and that's actually a really interesting point. And so for everyone, we're sort of like trying this methodology for radiation therapy a little bit different, because we're going to also look at combining it a little bit with machine learning and doing like some clustering in terms of the observations and how to, like, which observations are closer together, and derive how the doctors decide about the treatment plans for patients and what is the right way to do it. So Todd, you bring up some really good points on the feature reductions in the objective. If I think about it traditionally, how we do inverse optimization is that I know my forward problem, and I try to find out which of these features would be more important, and the doctors think about them a little bit more, given the different clusters of the patients that I have. So we're trying to recover those. And where I think, is interesting, and we have like back and forth numerous times, we have arrived at it, is that even the parts that we think we know, we usually don't write our forward optimization correctly. We think we do, but because we only write one model for everything, the model is usually too general and too restrictive both at the same time. So another thing that we back and forth come to it is that as we do the inverse learning, we learn more about the optimization. At some point, we want to change the forward optimization, the original optimization. In this arc, I had the constraints pretty set. But in reality, a lot of times we want to modify these constraints because we realize that they don't really align with what we see in reality, the observations and the decisions. So what is the right way to change it minimally so that it would align better? So Todd, I feel like your question alludes to that. I'm looking forward to our discussions tomorrow to talk more about this. I guess on the high level would be, yes, we can try, although traditionally that's not how we would do it.
Yeah, I guess, and maybe I'm wrong, but perhaps the corollary to your example would be if we were to measure, the carbs and the sugars, and then, but really what we were trying to find the optimal distribution of was the number of carrots and the number of cakes, right? Because that what you eat in cake is a function of, or what you put in with cake is, a function of all the, the carbs and sugar and stuff that are inside it. And so you're kind of optimizing one layer different.
Yeah, so I think that's why I'm excited to do the radiation therapy with the other method. So we're going to use a method that is not exactly this one. It's more integrated with machine learning, because I think some of those we can pick up with predictive analysis. So let me step back a little bit for everybody to explain. Here, the diet problem, it's easier than the radiation therapy problem, because in the diet problem, you can just write the problem in a linear format. The radiation therapy problem, what you actually care about is nonlinear. So what you do is that you have these reduction features that are linear, and you solve for those reduced features. And we've been doing optimization for radiation therapy for years now. Now, the question that Todd is asking is that, well, now that I'm recovering my optimization, can I do a better job than those linear things that we typically use? And I think that's an opportunity when we're looking at because we're going to look at the data both from optimization and also with machine learning. That's an opportunity to capture some of those nonlinear and highly complex, I guess, metrics that we want. And then maybe we will find a better way to embed them in the optimization and keep it linear. Or maybe if we can do the back and forth, we can guide the optimization indirectly to be closer to what we eventually care about, not just the things that are in the optimization.
Perfect. Cool.
Awesome. Future research. I'm excited about that one.
So I have another question, Kimia. Sorry, I'm trying not to monopolize the question time here. So, so you want to, so there's somebody out there who is trying to make optimal decisions. You want to reconstruct in some sense what they did. That's the general takeaway I took from this. And so, and you also mentioned economics lit, and we've talked about reinforcement learning a little bit. And so there's all these methods that people have thought about for how an agent could make optimal decisions from data that you could then reconstruct. So for example, one thing you could do is you could say, well, I'm just going to have this complicated regression model and with a bunch of features to personalize things. And my action is one of the features, and I could learn that regression. And then maybe you can try to reconstruct what it is that I was doing. Or you could do it the way reinforcement learning people do. So they're not doing a regression, they're doing something else. And then there are people in economics who solve these like cyclic equations sometimes. That's the third way, and people in causal inference have a fourth way of doing it. And so my question is, for what classes of algorithms for making optimal decisions that the agents could follow can these kinds of methods be used versus not?
Yeah, that's a good point, and that's why I'm excited to also like discuss with you tomorrow on all of this. The way that I think about it so this is an ongoing work. We're trying to we're at the beginning of really understanding what are the strengths and weaknesses of inverse optimization and inverse learning versus everything else that has been going on, and what are these connections. So some of your questions are really on point, and I guess as a field, we're still trying to figure those out. To me, one distinction between them is that all the other methods that you mentioned, they're typically unconstrained. And bringing in constraints that are, again, like I use knowledge base, but basically things that you don't necessarily see in the data, but you're aware of it. That's something that are hard to do in all the other ones. And that seems to be the separating factor between them. So I would say that I would do inverse learning when I have a highly constrained situation that is not necessarily reflected in the data. So for instance, in radiation therapy, we have doses that has to go to different organs, and if you just look at the data, you don't necessarily see that. In diet, again, you have the nutritional constraints. So that's where I see the distinction. I'm pretty sure there will be a lot of overlap as well. Again, I'm not thinking of it as in everything else go away, this is the way that we should do it. I think there are a set of problems that are better suited for different methodologies that we have, including the inverse learning, and it's part of the research. So hopefully, if you ask me again, in 3-4 years, I would have a really good answer for you. It's yeah, exactly this and that and that. Right now, this is my best guess and best answer that I can give at the moment. Does that make sense? I want to hear your talks. Honestly, tomorrow will be awesome.
Right, but I mean, but is it regressions that you're doing now? You're decisions based on regression problems?
No, we're not really doing regression. So in regressions, you look at a very specific type of optimization. You're looking at usually a least square optimization with, if you're looking logistic, nonlinear metrics, and you don't have constraints. If you have constraints, you usually use the Lagrangian to bring it up to your objective and solve that. So you cannot have hard constraints. So I would say this is not regression, as in we are not trying to find the best fit to the observations. That would be the first thing. That would be being very close to the observations. So we're adding all of these hard constraints, and then we're trying to pull it away from those and end up at the boundaries, closer to the actual thing that we know that should happen. That's why we have the trajectory.
Okay, thank you.
So Kimia, I think this discussion just goes to show what you're doing is totally interesting for everybody involved. It seems like it could go on for quite a while. Unfortunately, our time is up, so let me just take this opportunity to thank you so much for presenting and getting these ideas out there. And I look forward to continuing the conversation with you in other venues.
Thank you so much, and thank you everybody for attending. This was great, and I really enjoyed the conversation. Thank you.
All right. See y'all. Take care.
Okay, bye.
Take care. Bye.